I'm sharing my screen. Yeah, I will share my screen. So in the last class we discussed about the I2C protocol. So today we'll see the coding part. Okay. So we already seen like just I'm revising this I2C protocol. So here what is the operation it is operating, and the physical layer we discussed. Okay. And next we discussed about the operation like start condition. Okay. Start condition means HDA will go from high to low first, and SCL will go from high to low next. Stop condition means HDA will go from first, SCL will go from low to high, and SCL will go from low to high. Okay. So this is logic ones. Okay. So HDA is actually data line. Okay. SCL is clock line, and HDA only transmit when SCL is low. Okay. So this is the total protocol we already discussed, like first start condition. Okay. So HDL will go from high to low, and SCL will go from high to low, and after that it will need to identify the address, I2C address. So this is a 7-bit address. Okay. So each, and you have multiple masters and multiple slaves, so you need to identify the master and slave with a specific address. And next read by write bar signal. So suppose master want to write the data, so read by write bar equal to 0. So master want to read the data from the slave, then read by write bar equal to 1. Okay. And next ACKT. Okay, this is the acknowledgement from the target device. Okay. So whether target device is give the acknowledgement that so is it slave is ready or not. Okay. So master can read the data or write the data, no. So master can conclude that whether the slave is ready or not. And you are sending 8 bits of data, so that is a single byte communication. And next there are like two types of acknowledgements are there. One is ACKT and ACKC. ACKT is coming from the target device, so coming from the slave. Okay, write to the target for write operation. And ACKC is comes from the controller. Okay, after the master reads the 8 bits of data, so master will give the acknowledgement to the slave that reading operation is completed. So that is ACKC. Okay. And next is stop bit. Stop bit means what? Once first SCL should go from low to high, and HDA should go from low to high. So when it is high only, the I2C bus is idle state. Okay. So when it go from high to low, then it will be in busy state. Okay. The I2C bus is busy state. That we discussed in the last class. Okay. So we'll go with the coding part. So if you see the coding part, if the concept is fine, just want to check I2C concept is fine. Shall I move forward? Yes or no? Please give response. Yeah, hope this is fine. So I'll move forward. So coming to the coding part. Okay, if you see the coding part, so this is the code. So first module, what is my module name? IIC controller, I2C controller. So you are declaring input wire clock, input wire reset, and slave address is how many bit? 7 bit, no. So I am declaring the slave address also. Slave address is, so this is write operation. Actually this is actually write operation. For declaring this, you need to declare the slave address, that is 6 down to 0 means how many bits? 7 bits. Okay. And 8 bits of data. So 8 bits of data is transmitted, that is input wire 7 down to 0 data. And as I told you in the last class, there are two signals are there. Okay, I2C. One is HDA, serial data line, and SCL, serial clock line. Okay, serial data line is what? This is bidirectional. Okay, so this is bidirectional means what? We need to declare with the in-out. Okay, there is a port in the port rule connections we already discussed. There is an input port, output port, and the bidirectional port is a in-out port. Okay, serial data line is so master can write the data into the slave target device, or master can read the data from the slave. Okay, read or write operation is happening. That's why that data line, whatever the data line is there, that is bidirectional. That's why I am declaring with in-out, and this is a wire data type. and so I'm declaring all the inputs with Y data type, output with reg data type. Why? Because this serial clock line I'm using in the behavioral procedural block. That's why I need to declare with SCL with the reg data type. Okay. And next, state encoding I am declaring with local param. Okay. So so what is the difference between parameter and local param? Means parameter means we can override the parameter. Okay, we can change the size. So in the RAM I told you, so dynamically we can change the size. Okay, but local param we can't change the size. So local param means what? This is applicable for this code only. Okay, so I'm declaring local param. So total how many states are there? One is idle state, start state, and this is the address. Okay, so send slave address. Okay, send slave address. This is 4 tick so decimal 2. I'm declaring the states. Okay, slave address is 7 bits only. No, so that slave address is so idle state I'm declaring with 0, start state I'm declaring with 1, and send slave address I'm declaring with 2, and next is acknowledgement. No, so acknowledgement so coming from the slave, that is acknowledgement weight, that is 3, and send read write bit. Okay, that is 4, send read write bit. After read write bit there is a data is 5, and next read data is 6. Okay, this is for sending the data. Okay, writing the data, and this is for reading the data. Okay, after reading the data again there is acknowledgement. No, so data acknowledgement weight is 7, and next one is stop condition, that is 8, and done means 9. Okay, so I declared all the states. Total how many states are there? Total 10 states are there. Okay, so I declared with a local param. Okay, after that you need to declare present state and next state. Okay, this is like a FSM only. Okay, so what is the present state? I'm declaring with 4 bits, that is reg 3 down to 0. So state is the present state, and this is the next state. Okay, and next data register. Okay, so I'm declaring one data register, and next data register means in order to store the data I'm declaring with 8-bit value, reg 7 down to 0, data register, and slave address also I'm declaring with one intermediate variable with reg data type 6 down to 0, that is how many bits? 7 bit. Okay, and one more, bit counter. Every time when it is going from one state to other state, bit counter should increment. Okay, so for this I am declaring one more bit counter, that is 3 bit, 2 down to 0, and one more read write bit, this is 1 bit. Okay, I am declaring, and next SDA drive I am declaring, SDA data. Okay, again acknowledgement receive. Okay, and one more counter also I am declaring, SCL counter, that is 10 bit. Okay, counter means it will count this number of states. Okay, this bit counter is for incrementing. Every time when it is going from one state to other state, this bit counter should decrement. Okay, so this is for like initially it will be initialized with the 10, so it will be like decremented. Okay, so this is the initialization part. Okay, this is the initialization part, all this initialization part. Okay, and next this is the code for SCL clock driver. Okay, so always at the rate passage of clock or passage of reset begin. Okay, so this is asynchronous active high reset. Okay, asynchronous active high reset begin. If reset equal to 1, SCL counter will be initialized to 0, so 10 tick decimal 0, and SCL should be what? 1 only. So initially like when I2C bus is in idle state, so SCL and SDA should be connected to what? High, no? So that is connected to what? 1. Okay, else if, okay, end. Okay, end. Else if SCL counter will begin with what? 10 tick decimal 9. Okay, 10 tick decimal, so 9 begin. So SCL counter is initialized with the 10 tick decimal 0. Okay, if SCL counter equal to 10 tick decimal 9, SCL counter will be non-blocking with 10 tick decimal 0. Then SCL clock equal to what? Not of SCL clock. Okay. Else begin SCL counter equal to what? It should increment. Okay. So this is for clock generation of like clock divider circuit. Okay. We need to generate the clock for SCL, no? So for this I am writing the code SCL clock divider. Okay. And HDA line control. So assign HDA equal to, that is initialized to, this is ternary operator. Okay. So I am using the ternary operator with assign statement. Okay. If so, assign HDA equal to HDA drive, then HDA data will be allocated to HDA. Okay. Otherwise it will be in high impedance state. Okay. If HDA equal to HDA drive, okay, we already initialized HDA drive, no? Reg HDA drive. Okay. So when HDA equal to HDA drive, so HDA data, whatever the HDA data is there, that is allocated to what? HDA. Okay, that is allocated to HDA. Okay, HDA also we declared, no? Where we declared HDA. So this is HDA. Okay, HDA is 1 bit. Okay, so HDA data that will be allocated to HDA. Otherwise, it will be in high impedance state. Okay, so this is for HDA line control. Next, we will begin with state machine. Okay, finite state machine. Always at the rate passage of clock, passage of SCL or passage of reset. Okay, passage of this serial clock line or passage of reset. This is asynchronous active high reset. Begin. Okay, if reset equal to 1, begin. What is that state? It will start from the idle state. Okay, so slave address register is non-blocking with slave address. So this will initialize from the input, and whatever the data that will be allocated to data register, and the bit counter will be allocated to 6, and acknowledgement received is 0. Okay, when it is acknowledgement received is 0. So now it will, so HDA data will be 0 and HDA drive also will be 0. Okay, so this is actually the values when power on reset. When you apply the reset, so what are the initial states? That is idle state. What are the bit counter values and ASIC received HDA data and HDA drive. So these values will be there. Okay. Else begin. What is the next? What is the state? Else if reset equal to 1 means it will be in the initial state. If reset equal to 0, if this condition is not satisfying, it will go to the next state. What is the next state? So that means state equal to next state. State equal to next state. So in the FSM finite state machine, we already discussed. That means present state logic is sequential in nature. Okay, this is the state machine, means present state logic. Okay, sequential in nature. Okay, and next state logic is what? Combinational in nature. So this is the next state logic. Okay, so this whole thing is next state logic. Okay, so next state logic you see always at the rate star. Star means what? Implication operator. So when you are applying the star, so it will be applicable for all the inputs. If there any change in the inputs, then there is a change in the outputs. Okay, so as I told you, suppose if you have the design have like 250 inputs or like 300 inputs and like 500 outputs. Okay, so you can't declare all the inputs in the sensitivity list, no? So in order to declare that, you can use this implication operator star. Okay, so always at the rate star means wherever you are using the inputs, so these many inputs are there. Okay, how many inputs are there? These many, like 5 inputs are there. Okay, so you not declare, so it is like difficult to initialize all these inputs in the sensitivity list, no? So that's why I am using the implication operator, that is star. Begin. If reset equal to 1, what is the state? Next state equal to idle state, and HDA drive equal to 0. HDA data is what? HDA release HDA to high. Okay, bit counter equal to 6 and acknowledgement received equal to 0. Okay, this is when reset is equal to 1. Else begin. If reset equal to 0, next state equal to what? State. Okay, and HDA drive you need to drive to 0 and HDA data equal to 0. Okay, so this is for always at the rate. Again, I'm starting with case statement. Okay. So this is default HDA is high means what? Idle state. Okay. HDA equal to high means what? Idle state. Okay. So when it will go to the start state, first HDA will go from high to low. After that, SCL should go from high to low. That is the start state. Okay. So case state. Okay. Case state. Idle state. Idle state begin. So HDA drive you should make as 0. HDA data you need to make as 0. And read by write W, so RW bit also making as 0. So set 0 means what? For write operation. 1 is for read operation. So default is what? Write operation only. Okay. Default is master is writing the data into the slave. Okay. So what is the next state? Start state. Okay. So this is the idle state. Okay. Again it will go to the start state. Start state begin. So HDA drive we need to make as 1. HDA data. HDA is actually HDA data is here we already seen, no. So that is HDA is initialized to HDA data, no, where here HDA line control. HDA drive, that is HDA data is initialized to HDA, no. So here in place of HDA what I am using HDA data only. So HDA data equal to 0 means what? This is the start condition. So HDA will go to low. HDA will go to low. Okay. So next state. What is the next state? Send slave address. Okay. After start state, there is a slave address state. Okay. Slave address state. So next you see. So this is the send slave address. Okay. So begin. Say slave address equal to 1. HDA underscore data, that is equal to slave underscore, this is a combinational, that's why we are using blocking assignments. Okay. So combinational in nature, no, that's why in this I am using in the, so next state logic is a combinational logic, that's why I am using blocking assignments. Okay. So one after the other instruction will be executed sequentially. Okay. So HDA data, that is equal to what? HDA address register bit counter. Okay. So that means output slave address bit. So whatever the slave address bit is there, that is coming to HDA data. Okay. If bit counter equal to 0 and SCL equal to 0, okay. So next state equal to what? ASIC wait. Okay. After getting the address, so it should wait for the acknowledgement. Okay. So that is acknowledgement coming from the target device. Okay. It should come from the slave. So transition to acknowledgement when SCL is low. Okay. Else if SCL equal to 0, begin. Bit counter equal to what? It should decrement. I told you, no, bit counter should be start from 9 and it should decrement, no. So bit counter equal to bit counter minus 1. Okay. For every state, bit counter will be decremented. Okay. So this is for slave address. Okay. And after that, acknowledgement. Okay. So if you see the acknowledgement, so during this acknowledgement we need to release HDA. HDA drive we need to make as 0 and SCL equal to 1. Then ASIC received equal to what? HDA equal to 1 tick binary 0. Okay. This samples HDA during SCL is high. Okay. So $display. So this is display in the TCL console. So ASIC wait, time, SCL, HDA, ASIC received. I want to see in the TCL console, this can be displayed. Okay. And if SCL equal to 0 and ASIC equal to 0, begin. What is the next state? So this checking for this condition. Okay. When SCL equal to 0 and ASIC received. So acknowledgement is received. Okay. Then master should decide whether to write the data or read the data. Okay. So what is the next state? Next state equal to what? Send RW bit. Okay. So what is this statement? Proceed if ASIC is received. Okay. Proceed if ASIC is received. And else if, okay, SCL equal to 0. Suppose only SCL equal to 0. So what is the next state? Stop state. So that means when acknowledgement is received from the slave, then master should write the data or read the data. Okay, it should do two operations. Okay, master should write the data into the slave or master can read the data from the slave. Okay, suppose ASIC is not received, so slave is not ready. Okay, so ASIC is not received. Then what it should go to? So it should go to the stop state. So master should go to the last state, that is stop state. Okay, so this is what this is for acknowledgement. This is the state for acknowledgement. Okay, next state. If you see the next state, send read by write bar bit begin. So read by write bar bit in this HDA drive I am making as 1, and HDA data equal to what read by write bar, so RW bit. Okay, this send RW bit. As I told you, like read by write bar signal equal to 1, it will do read operation. Read by write bar equal to 0, it will do write operation. Okay, so I am checking for the condition. See here, if read RW bit, if RW bit, that means RW bit equal to 1, then read data will be given to the, it will go to the next state. What is the next state? Read data. Okay, so I told you, if read by write bar equal to 1, transition will go to read data. Okay, and else begin, else read by write bar bit, read RW bit is equal to 0, it should go to next state. What is the next state? Send data. Okay, so when read by write bar equal to 0, transition should go to where? Send data. Okay, and end bit counter equal to what? 7. Okay, so reset the bit counter. Okay, this is for send read by write bar signal. Okay, simple. Like when read by write bar equal to 0, it will do write operation. When read by write bar equal to 1, it will do read operation. Okay, next, suppose if it is send data, means what? Master writing the data into the slave. Okay, so next state is what? Send data. In this send data, what you are doing? HDA drive equal to 1. I am making HDA drive equal to 1. HDA data, that is equal to what? So I am getting the data register bit counter. Okay, so it will send the data bit by bit, as this is serial communication, no? So 8 bits of data. Okay, 1 byte of data is sending one bit by bit. Okay, it will send bit by bit. Next, if bit counter becomes, so bit counter I initialized to what? 7, no? So if bit counter becomes 0 and SCL equal to 0, so what is the next state? It should wait for after sending 8 bits of data, it should wait for the acknowledgement, whether the 8 bits of data is transmitted to master or not. So it is expecting acknowledgement from the slave. Okay, so what is the next state? Data acknowledgement wait. Okay, so transition to data acknowledgement after the last bit. Okay, it is waiting for acknowledgement from the slave. Okay, else if, okay, every time one bit is transmitted, so bit counter will be decremented. Okay, so bit counter will be decremented. SCL equal to 0 and bit counter will be decremented. Okay, this is the logic related to what? Send data. Okay, and coming to the read data, so in the read data you need to release the HDA drive equal to 0. If SCL equal to 1, then whatever the data present in the HDA, that should come into where? HDA register bit counter. Okay, so this is for what? So whatever the data present in the slave, that should come into data register bit counter. Okay, so if bit counter becomes 0, then so after reading the data, slave is expecting the acknowledgement from the master, that master read all the 8 bits of data. Okay, so it is waiting. So what is the next state? Data acknowledgement wait. Okay, data acknowledgement wait, and else if SCL equal to 0, so reading operation also happening bit by bit. Okay, it will decrement the counter during SCL low. Okay, this is read operation. Next, acknowledgement. Acknowledgement, if you see, HDA you need to drive to 0. Okay, SCL equal to 1. So ACK received equal to what? HDA, that is equal to 0. This samples HDA for ACK during SCL. Okay, so that means during acknowledgement, HDA we need to pull low. Okay, SCL we need to make as 1 and HDA we need to pull low. Okay, for displaying in the TCL console, I am using this. Okay, data acknowledgement wait equal to time SCL HDA what are these values I want to display. Okay, and if SCL equal to 0, ACK received. Okay, so acknowledgement is received. That means what? So master read the 8 bits of data. Okay, so master will send the acknowledgement that I received 8 bits of data. It will send the acknowledgement signal to the slave. Okay, then what is the next step? So reading operation is completed. Next, it will like ACK wait. It should go to either writing or reading operation. It should go to stop condition. Proceed to stop condition if ACK is received. Else if SCL equal to 0, what is the next state? Stop condition only. Okay, so this is what acknowledgement. Okay, and next stop condition. What is stop condition? So in the stop condition, SDA drive you need to make as 1. SDA drive is actually SDA equal to 1 only, and SDA data we need to make as 1. Okay, this is SDA you are making as high. Okay, and if SCL equal to 1, begin, what is the next state? Done means what? End of the transaction. Okay, so when SDA and SCL are equal to 1, those are said to be in idle state. Okay, so in the done, what is the next state? It will go to the idle state. Okay, go back to the idle state. End case, end module. Okay, so if you observe here, whatever the concept I told you in the last class, those states only there. So one is idle state, next one is start state, next send slave address, next acknowledgement wait. Okay, and read by write bar signal, and there are two operations can perform, means write data or read data. Okay, writing the data into the slave from master to slave, or reading the data from the slave. Okay, so this is write operation and this is read operation. Next acknowledgement, next stop condition, and in done means what? Again it will come to the idle state. Okay, did you understood any doubts or queries in this code? Shall I move forward? Shall I move to the test bench? Waiting for your response. Hope you understood this code. Yeah, I will go to the test bench. So TB file. So if you see the TB file, so module I2C controller underscore TB. Okay, so whatever the clock reset, SDA slave and SDA master, I need to declare with you need to declare the internal variables of the test bench. Okay, so I need to declare clock reset SDA slave with reg data type, and SDA master and SCL and SDA SDA is a means in the design we already seen SDA is a in-out, no? So in-out, when you have you seen in the port rule connections? Okay, so that is we need to declare with void data type only. Okay, as this is in-out in the design, so we need to declare with void data type only. And test slave address I am declaring with 7 bits with reg data type. Test data also I am declaring with 8 bits. Okay, this is the data. Okay. Next, I told you in the last class there are pull-up resistors are there. No, it is connected to VCC like that. So this is corrected pull-up logic for SDA. Okay. So what is the corrected pull-up logic? Assign SDA equal to SDA master equal to 1 tick binary high impedance and SDA slave equal to 1 tick binary high impedance. Then if this condition is true, okay, if this condition is true, then SDA will be what? High. Okay, initially what happens when it is in bus is not connected, I2C bus is not connected, it will be in open circuit, no? So that's why I am checking for this condition. SDA master is in high impedance with what? Open circuit. SDA slave is in high impedance. Then SDA will be by default it will be pulled high only. Okay, and otherwise SDA master is not equal to 1 tick binary Z. If it is not equal to high impedance, then SDA master is allocated to SDA, and also SDA slave also allocated to SDA. Okay, So this is for correcting pull-up logic for SDA. Okay. Initially, when SDA equal to high, then it will be in idle state. Okay. So during I2C when it is in operation mode or when it is in busy, so SDA first start condition we already seen. SDA should go from high to low, and SCL after that SCL should go from high to low. Okay. So this is my pull-up logic. And next you need to instantiate your design in the test bench. How to instantiate? So what is my design name? IIC controller, and instance name UUT. So this is connection by name. So whatever the variables outside the bracket are the design inputs and outputs. Whatever the variables inside the bracket are test bench variables. Okay. So this is instantiation connection by name. Okay. So in industry they will follow connection by name only. Okay. So like this vertically we need to write. Okay. Why? Because you have so many inputs and outputs. Okay. When you are using connection by position with order list, some input is missing, means it is hard to debug. Okay. Vertically means we can like so both can be same. Okay. Not nothing will happen. So vertically we can debug. Okay. So mostly prefer connection by name in the industry. Okay. And clock generation, initial begin, clock equal to 0, forever, #5, clock equal to not of clock. Okay. You are generating the clock with so 10 nano. So time scale we already given. Times, what is the time scale? 1 nanosecond by 1 picosecond. So this is 1 picoseconds is the precision, and 1 nanoseconds is time period. Okay. So time period is how much? It should be off for 5 nanosecond and it should be on for 5 nanoseconds. So that means what is the total time period? 10 nanoseconds. So if you find out the frequency, then that is 100 megahertz. We are generating a clock with 100 megahertz. And this is the slave behavior for the acknowledgement. Okay. So initial begin, first SDA slave equal to 1 tick binary Z. This is default to release. Wait UUT dot state, that is equal to UUT dot acknowledgement wait for the acknowledgement phase during the negate of clock. Okay. In order to avoid the setup time and hold time, I am using this during the negate of clock. What happens? SDA slave should be pulled low. Okay, for the acknowledgement. Okay. And at the rate passage of clock, release SDA for SCL high. So SDA slave will go to high impedance state. This is for acknowledgement. Okay. And I need to test the sequence. Initial begin. So what is the slave address? Slave address is 7-bit, no? So 7 tick H42. So I am declaring with hexadecimal. So 42 means what? So internally it will be stored in terms of binary. So 1000010. Okay, 1000010. This is the slave address. And example data I am declaring with 8-bit 10101010. This is for example for test data. Okay, I am applying the reset. Okay, I am applying reset equal to what? I am using asynchronous active high reset now. So when reset is applied, so all will come to the initial state. So I am asserting the reset. Okay. After that, after 20 time minutes, what I am doing? I am releasing the reset. Okay. I am releasing the reset, and dollar monitor means I want to display in the TCL console for monitoring purpose. If there any change in this variable, then it will display. And wait state. Okay, it will wait until done. Okay, it will be executed. State equal to what? Until state go to done state, it will be in the wait state only. Okay. After going into the done state, again dollar display, test is completed, dollar stop. If you want to pause the simulation, you can use dollar stop, end and end module. Okay. So this is the test bench. Is it fine? Test bench. First you go through the concept, then go through the code, then you can understand. Okay. First you go through the concept, how the working of, that's why I told you to go to the working of I2C protocol, no? So that's why you need to go to the concept, then go to this code, then you can understand. Okay. Yeah. So I'm executing in Vivado. So like project, new project, next. Okay. So here, So I'm going to this project name. Yeah, so where is this project? So here you see. So in the VLSI design, yeah, it's clearly there. And RTL codes using Vivado. Select. So what is my project name? Like you give the project name is I2C, no? So give the project name is IIC protocol or I2C protocol. Okay, you give the project name as what?